Today we're going to talk about the gravitational force. That is, the force exerted between any two objects that have mass. The gravitational force is represented by the following equation. The force due to gravity, or the weight of an object, is equal to the universal gravitational constant times mass 1 times the other mass. These are the two masses we're concerned about, divided by the distance between them squared. So this looks something like this. I have mass 1, mass 2, and the distance as measured from the center of mass for both of those objects. This equation, the equation for the strength of the gravitational field, it's force in newtons. It's what's known as an inverse square law. Force of gravity is very interesting in that it can act at a distance with no contact between the two objects. You or I can only exert a force if we physically touch an object. Because of the structure of this equation, it leads itself to a lot of manipulation, such as what happens if I double one of the masses or increase the distance by 2. How does that affect the resulting force? So if we set ourselves up a little table here, we can start to take a look at what happens here. G is a constant, so we can just assume that to be 1 for these types of problems. But if they tell me something where, well, what happens if I double one mass, keep the other mass the same, and keep the distance the same as it originally was? Well, for your original, just assume it was 1, and now plug those values into the equation, and remember it being an equation, the left-hand side needs to equal the right-hand side. So in this case, we have mass 1 is 2 times as big as it originally was. So in order to keep the equation balanced, my gravitational force must be twice as large. We could also do a scenario where both masses stay the same and I double a distance. Well, we plug that in. I have 1 times 1 in the numerator, but I have 2 squared in the denominator, which is 4, which means that gravitational force, if I increase the distance, if I double that distance, is 1/4 as great. This is what's known as, again, the inverse square law. The strength of the field, the force due to the gravitational field, is 1/4 as great when I double the distance between the two objects. Well, as we learned back a while ago, in addition to the force due to gravity equaling G mass 1 mass 2 divided by the distance between them squared, when we were talking about Newton's second law, we also looked at it in terms of m times lowercase g, or mass times lowercase g. So this allows us to set this up where I can arrange it such that mass times lowercase g is equal to capital G, mass 1, mass 2, divided by d squared. Well, the mass on the left-hand side of the equation, let's call it mass 2, is represented in the numerator on both sides of the equation. So I can divide both sides by mass 2, and mass 2 divided by mass 2 is just 1. And that will leave me with lowercase g equal to g times mass 1, that's the other object, divided by d squared. So the gravitational strength of the field, say exerted by the moon or Earth, would be, the moon or Earth would be represented by mass 1. And it can be calculated very simply by playing this out. This would be g mass of the big object, let's call it the moon here since we're colonizing the moon, and the distance is the radius of the moon. Squared. That will give me a value of g that anytime now I look at any other object on the moon, I don't need to go through the whole big equation there to find out the gravitational force acting on it. I can just use m times g. So this leads to an interesting concept which we'll talk about in a minute. We have capital G, which is the universal gravitational constant, is the same everywhere. It is a constant, a true constant. Lowercase g, which is a measure of the gravitational field strength around a particular object, varies depending upon what the large object is. It would be larger on Earth or smaller on something like the moon. So it's just important to remember. Now sometimes we talk about lowercase g as being the acceleration due to gravity, which works, and we just kind of treat that as that constant 9.8 meters per second squared. You've probably heard that before. Well, that's only true on Earth. The value anywhere else would be different, and actually that varies a little bit among regions of the Earth too. So it's not, lowercase g is not truly a constant.